And we use Wiener filters in noise reduction, especially in speech processing, image deblurring, channel equalization, and echo suppression, and so on. And its advantages are it is simple. So Wiener filter is simple and it offers a mathematically optimal solution. But it works under the stationary conditions. So it requires accurate knowledge of statistical characteristics and does not work well for the non-stationary environments. So Kalman filter, it is suitable for the non stationary environments. So it extends optimal filtering to dynamic time varying environments. And it basically uses the recursive prediction and correction structure. So recursive prediction correction structure it is. So it basically comprises with the two important stages or steps, prediction step and correction step. So prediction step, we estimate the next state of the system, and correction step, the estimate is updated using the incoming noisy and measurement. And Kalman filter is a powerful tool actually. So because it gives a minimum mean square error estimate in real time and adapts to system variations even. So we have different real-time applications for the Kalman filter, like GPS, INS navigation systems, 5G massive MIMO channel estimation, radar tracking, robotics. So and also even in the sensor fusions are for IoT. So many applications are there. But still, it has got some limitations. It includes the need for accurate mathematical modeling and also Gaussian noise assumptions and increased computational complexity compared to the Wiener filters. So these are these two are some of the important things, and optimum filtering aims to minimize the estimation error, and the Kalman filtering is the optimum filter for time varying state-based systems, and it provides the best estimate of system states using the recursive algorithm. So, which basically forms the backbone of an important theory, which is known as the estimation theory. So, many applications in science and engineering require estimation of the states of a system that changes over time using sequence of noisy measurement made on that particular system. So, estimation theory is since Kalman filter means it is an estimator. So it is going to find the future behavior of any dynamic system. So the backbone for this one is it forms the backbone for state estimation theory. So it has been a fundamental tool. A state estimation theory is the fundamental tool in fields like communication, signal processing, ocean and space research, and biomedical engineering. And many problems in science and in engineering requires since estimation of the states of system that change over time. Uh, as we mentioned that using a sequence of noisy measurements made on that particular system. So state estimation is one of the best mathematical approaches. So, in order to aim, it basically aims to analyze the variance in the states of the system or process. So, and it is employed to produce the best estimate of the true state of the system. So, estimator is a tool that predicts the future behavior of a model from the available information. So based on the available information, it is going to predict the future behavior of a model. The modeling and performance analysis. So performance analysis means it is completely based on the simulation results of various nonlinear estimators. It is carried out here. So, system models of various nonlinear estimators and applications of these estimators for different real-time applications and their performance analysis in terms of speed of convergence or error performance and all these things. And the state estimator concerns the problem of estimating the probability density function for the state of a process which is not directly observable. So this involves both predicting the next state and applying the corrections based on the measurement equations. So here actually the two important things in state estimation is state as well as the estimator. State means the state of a system gives the complete internal condition of the system at any given instant of time and is represented mathematically by a numerical vector. So suppose, for example, let us consider an electric motor. So this is a system. So this is a system. What are the states of electrical motor participants? Anyone? What are the states of electric motor? So which basically includes the states of the electric motor basically includes the current through the windings or position or speed of the motor shafts, etc. So for our engineering applications, suppose for an orbiting satellite, the present position of the satellite, present position means which basically requires a range, azimuth as well as the elevation, right? And velocity, acceleration. So these may be the states. And the states of underwater vehicle, if you consider, so that may be their range, speed, bearing, course. So these comes under the states of the system. So even for biological system, the blood sugar levels or heart and respiration rates becomes the states. So if you see in all these examples, the states of each system gives the complete internal behavior of the system. So therefore, the field of estimation theory can virtually apply to any field of science as well as engineering. Okay. So the estimation of states for engineers are important for two reasons. So the first one is to implement state feedback controller. So for example, suppose if you consider if you want to control the velocity of a satellite, if you want to control the velocity of a satellite, the aerospace engineer needs to estimate the altitude of the satellite. And in order to control the position of the shafts of the electrical, shafts, the electrical engineer needs to estimate the currents through the windings, right? So this is why actually the state estimation is important. And sometimes what happens is the states are interesting in their own right. Like sometimes the engineer wants to know the condition of the system. Suppose if we need to estimate the internal behavior of a system using state estimation algorithms, an aerospace engineer needs to estimate the position of the satellite in order to properly schedule its future activities. Okay, so therefore, the state estimation plays very important role to find the future behavior of any system or process. The mathematical modeling of this view of state estimation is shown here. You can see the mathematical view of the state estimation. So for a specific application, so see here, it comprises with the three modules: the dynamic system and measurement system and the state estimation, the state estimator. So here the dynamic system gives you the states of the system based on the system error source. So the dynamic system means like an electrical system or mechanical system or communication system or biomedical system, anything, any system. So it has basically some internal variables, right, which are called states. So just now we have discussed for a satellite, it's a velocity, position. So these things are the states. So the dynamic system estimates the states like its position, velocity or temperature, voltage, concentration, all these things. But the thing is, these states are not directly measurable. Okay, so they must be estimated using available measurements. They must be estimated using available measurements. So here, taking the measurement errors into account, the measurement system provides the measurements. And here the state estimator takes the measurements into account and take the previous information and gives you the future state of that particular system. So this is actually the thing happened in the state estimators. This is happened in the state estimator. So the dynamic system generate the system states based on the taking the system errors into account and measuring system. So suppose if you consider the satellite system. So the input states of the satellite system, suppose if you consider that it's a position, velocity, or acceleration. Okay, so these are the states of the system, and these states are continuously monitored by a measurement system like a radar. So radar will always monitor the states of this satellite system. Okay, so considering the measurement errors also into account and gives the measurements here. Okay, so that means what is taking the measurement errors into account, it gives some measurements here. So taking these measurements and previous information, the state estimator is going to give you the future state of the system. So that means suppose xk is the a priori state, and taking the measurements, the previous measurements into account, present measurements into account, xk plus 1, which is the future state of that particular system, dynamic system. So what is the next position of the satellite is going to be given by this state estimator, taking the previous information as well as the measured information, like estimating velocity from noise position data, or estimating heart rate, suppose in the biomedical applications. So it is going to estimate the heart rate variations from ECG, or estimating channel coefficients in wireless communication, or estimating glucose level in biomedical devices. So this is actually the important mathematical view of this state estimation. Okay, so to do this systematically, the entire mathematical representation, so the it basically requires a tool, mathematical tool. So here we have the different state estimators. Here I have mentioned some of the state estimators, like Kalman filter is one such state estimator, extended Kalman filter, uncentered Kalman filter, particle filter, interacting multiple model filters. So based on the application, based on the constraints, specifications, we may choose one among the different types of state estimators even. So here, as I have mentioned, this state estimation needs a mathematical tool. It requires a mathematical tool. So a dynamic system has uh, what we call the state estimation, which is a mathematical framework, is required to describe how dynamic system evolves over the time. So state space model is such a model. So dynamic system has internal variables, right? Which are called states, like its a position, velocity, temperature, voltage, and so on. So these states are often not directly measurable, as we mentioned. So we must be estimated using available measurements. We must estimate them using the available measurements. So which can be done by using a special tool, mathematical tool, which is known as the state space model. So estimation, Kalman filtering can be done through a specific theory, which is known as state estimation theory. And the state estimation requires a mathematical tool, which is a state space model. State space model is a tool in order to measure the state estimations, in order to measure the state estimations. So in order to perform the state estimation, as we require a mathematical tool. So any system that concerns with the mathematical modeling is likely a candidate for the state estimation. So the tools of mathematics can be used for modeling, and thereby control the states of the process, and can find the information about that particular process. So, state space model is one such best mathematical tool in which the states of the system are represented by a numerical vector, and is very important for current researchers even. So, we can use this state space model as a mathematical tool for many applications even. So, we have the different state space models. So we have two different state space models, linear models as well as the non-linear state space models. So based on what type of system it is, whether the system is linear system or non-linear system, we can adopt the linear model approach of mathematical model of state space model or non-linear state space model. So many researchers have concentrated on linear approach as it is simple, but most of the real world problems like tracking or navigation applications, so they are completely non-linear in nature. So because the dynamics of the system are completely non-linear. So some problems have linearization, which is uncontrollable near interesting working fields. So linearization is not effective in such cases. And some problems are simple and valid, but its validity is confined to finite domain only. And some problems are completely external, so where the linearization is ineffective in that particular case. So uh, we are going to concentrate especially on the non-linear models only, non-linear models. So system models, these state space model concern with two submodels even. The state space model is subdivided into two model. One is the process model and measurement model. So the complete mathematical approach of state space model comprises with the two submodels: process model, which is also known as the propagation model, and second one is measurement model or observer model or otherwise. So this propagation model or process model, so it describes how the state propagates in time based on the external influences like input or noise, how the state propagates. It gives how the states propagate. Whereas a measurement model, so this model describes how measurements are taken from the process, so typically simulating noisy measurements. So these two submodels are defined both for the linear as well as the non-linear process. But the way of representing mathematical formulation is different for linear and non-linear process. But for any linear system or non-linear system, these two models are very important. So if you see, this is the linear state space model. So as our ultimate goal is to estimate the future behavior of the system, right? So xk plus 1 is equal to ak xk plus bk uk plus wk. This is the propagation model. If you observe, this is linearly, it is a linear fashion. It is arranged in the linear fashion. And measurement model, so this is also linearly elevated, right? So here these functions can be expressed by using these matrices A, B, C, W, and V. So these W and V indicates the propagation noise, and V indicates the measurement noise. Measurement noise. So if you see the nonlinear state space model, so here the future state is expressed as a function of the three variables. So xk is the present state. UK indicates the input state. WK indicates noise. So similarly here also, xk is the input state and vk indicates the measurement noise. So if you observe here, the future state is expressed as function of these three, whereas in the previous case it is a sum. So it is a summation. So linearly approximated. So the next state is given as a linear combination of state, input, and noise, whereas here it is non-linear function. It is a function. So Kalman filter basically adopts this state space model in order to find the future behavior of the system. So Kalman filter is a well-known adaptive filter algorithm, widely used for the tracking applications especially. So here in the Kalman filter, so we use the linear combination of state, input, and noise, and also the observation model is also represented as a linear combination only. Linear combination only. So here, this is actually the Kalman filter steps. how actually we are going to deal with Kalman filter. So initialization, and it involves the predicting the prediction and updation, taking the new measurements into account, and again the process continues. So this is the Kalman filter, and the prediction can be done through these mathematical expressions. So the posterior information from the a priori information, how they are going to be predicted, and how the correction is going to be considered by taking the Kalman gain KK. So these are the things. So here I'm going to explain it with respect to one example. So suppose if you consider a vehicle which is going in a straight line, vehicle which is going in a straight path. So this is the vehicle. Okay. So we want to mathematically model how a vehicle moves along the straight path. So in this particular case, first you have to observe what is the input and what are the state variables, means states, and what is the output. So participants, can you give any inputs? What would be the input we have to give in order to move this particular vehicle, students, participants?
Force.
So acceleration, we need to give acceleration, right? So acceleration becomes the input. So this acceleration basically controls the velocity. So input is velocity, which is controlled by the acceleration. Obviously, output is the measured position. So here are the state variables are position and velocity are the state variables. Position and velocity are the state variables. So this is actually the standard example in Kalman filter theory, which represents a linear dynamic system. So for a linear dynamic system, I think everybody is aware of. So we'll use kinematic equations. So we have three equations. The V is equal to U plus AT, and S is equal to UT plus half AT square, and V square minus U square is equal to 2AS. So we are familiar with all these three equations, right? So we are using these two equations since our state variables are position and velocity. So here the position S is represented as ut plus half at square, and velocity is represented as u plus at. So xk is the state variable, the state of the system, and the variables sk and vk, which are position and velocity, are represented like a state vector sk and vk. And our ultimate goal is to find the future state of the system, future state of the dynamic system or a vehicle or whatever it is. So the position, the future position is the previous position plus this ut plus half at square. And also here we have introduced the noise component, that is the process noise. This is the process noise. And similarly, the velocity is, so the velocity is previous velocity, initial velocity plus at plus wk. So which indicates the process noise. So these two equations are propagation model in our state space model. And now in order to update the states, we need the observation information or measurement information, where the measurement information is given by y. So measurement information is given by y. So here if you observe, so this is xk, right? So you can represent xk plus 1 by using these two equations. By using these two equations, xk plus 1 can be defined using a linear state space model. Linear state space model. So xk plus 1 is sk. So the matrix and sk and vk, right? Sk and vk. So sk is, the coefficient of sk is 1 and coefficient of vk is t. Okay. So therefore here it is 1 and t. And Vk plus 1, for Vk plus 1, since there is no coefficient for Sk, since it is independent of this position, so the coefficient for Sk is 0 and coefficient for AK is, the coefficient for Vk is 1. Coefficient for Vk is 1. So Xk plus 1 is defined as 1 T 0 1 and Xk. This is the previous state Sk and Vk plus the input state. So the input, what input we are going to give is acceleration. So for Sk plus 1, the acceleration is Ak t square by 2. So the coefficient of Ak is t square by 2 and the coefficient Ak is here is t. So t square by 2 and t square by 2 t Ak. So this is input state. This is previous state and this is input state and this is noise. Wk is the noise. And now yk is the output state. So output is obviously 1 0 since output is the position sk and vk. So the output is position only. So therefore 1 0 xk plus this zk indicates noise in measurement system, measurement noise. Wk indicates process noise, zk indicates measurement noise. So here the complete these noises are represented by the autocovariance of the process noise, which is given by expectation of wk transpose, and autocovariance of the measurement noise, autocovariance of measurement noise zk transpose. So the covariance between the positional noise and velocity, so we have to calculate. So even for the within the position we have the noise and velocity we have the noise, and also covariance between position noise and velocity has also to be considered, since covariance is a statistical measure, right? So that tells you if they increase together, positive covariance. If one increases while the other decreases, negative covariance. If they are independent, zero covariance. So, these covariances indicates the noise interference in the system, noise interference in the system. So, in this, so this is how we can first model the system, dynamic system. So we have considered the system as a vehicle which is going in a straight line. So for that system, using these kinematic equations, we have modeled the system. Model the system using state space equations. And then we have to find out the what we call the estimation we can do it. So in this example, so let us consider the acceleration is 1 feet per second square, and standard deviation of acceleration is 0.2 feet per second square, and position is measured with an error of 10 feet at 10 times per second. So that means we are taking the measurements 10 times in a second, 10 times in a second. So the complete the efficiency or the performance of the system depends on how good the measurements are, how good the measurements are. So you can take 10 measurements per second, or 100 measurements per second, or 5 measurements per second, like that. So based on the accuracy that we require and based on the system specifications and all, so we can have the measurements, we can take the measurements. So since we are using simulation only, so you can take the you can use different measurements. Okay, so that you can compare the analysis, you can compare the performance analysis of the system for different measurements even. So but other things also, so if you increase the number of measurements, obviously the computational complexity increases anyways. So here A is equal to 1 feet per second square acceleration is given, and noise in acceleration, that is the standard deviation, is 0.2 feet per second square was given, and here time taken for each measurement is obviously 1 by 10, so 0.1 second. So the measurement is taken for every 0.1 second. And here you can replace t is 0.1. So from the previous thing 1 t 0 1, so you can replace t with 0.1, and t square by 2 t. So here we have replaced all these things. So we have given the real time values for this state space model. So we know that S is equal to ut plus half at square, right? So S is proportional to the acceleration. So S is proportional to acceleration. And V is proportional to, here also V is proportional to acceleration. So you can observe these things. So Y means, so since we need to provide the system noise, propagation noise. So the noise due to propagation noise, the propagation noise, that is the variance of position noise is proportional to half a t square, that the sigma a into t square by 2 whole square. Since s proportional to a t square by 2, s square proportional to a t square by 2 whole square. So sigma s square proportional to sigma a t square by 2 whole square. So here sigma a is a standard deviation, that is the noise content, so which is given by 0.2 feet per second square. So therefore it is 0.2 into, so that sigma s square is 10 power minus 6. In the similar fashion, the variance of the velocity is sigma v square. So that means positional noise, here we have calculated the positional noise and velocity noise, only positional noise and velocity noise. But the thing here is the covariance between positional noise and velocity has to be calculated, so which indicates how errors, so errors means uncertainties in position are related to errors in velocity. Okay, so that's why here the covariance of position noise and velocity is given by this equation. So during the position, how this velocity interferes. So that can be done by the covariance of position noise and velocity. So which is given by the product of standard deviation of positional noise, position and velocity. So already we have calculated the standard deviation variance for these two things under roots. Here we have considered, so that the covariance we have calculated here. So the covariance matrix is given by expectation of WK transpose. So WK transpose means WK indicates what is this? Noise standard deviation in position, standard deviation in uh, VW, standard deviation in velocity, and here it is, it's a transpose. Okay, so that we'll be getting SW square, SW VW, VW SW, and VW square. So which indicates the covariance matrix. So this covariance matrix is, it indicates the noise, the propagation noise, the propagation noise. So here this WK is replaced with this propagation noise matrix Q. So now we will use all the Kalman filter equations, so prediction and updation, so which can be done by all these equations. Okay, so these are the equations. So once I have given all these equations and calculate after giving these equations and running the MATLAB code. So these are the results I've got. These are the results I've got. So this one indicates the true state, and the green line indicates the measurements, where the measurements are taken, 10 measurements are taken per 1 second, that is 0.1. second one measurement, and this black line indicates the Kalman filter. So if you observe the true state and the Kalman filter, after estimating it, the Kalman filter achieves in estimating the true state. Okay. So this is how actually we'll use a state estimation. So that means the future estimations can be made by using the Kalman filter, using these state space models. So this Kalman filter is optimal estimate for linear system models. So this filter is a optimal filter, but it is applicable only for the linear systems, linear models. So where the input and states, everything is linear in nature. And one more thing here we have considered is noise also. Noise is also linear noise and additive noise. Additive noise means we can consider the Gaussian noise only. So for non-linear states, non-Gaussian noise, the Kalman filter won't work. So only linear for linear applications only will use the Kalman filter. So for non-linear applications, we can use some other Kalman based filters are being used, which are known as extended Kalman filter, uncentered Kalman filter, particle filter, and interactive multiple model filters. So different filters are there, but the thing in here is the basic concept involved in this all these filters are like state space modeling only. So this is one of the fine mathematical approach. So so I'll show one video, students, to you. Is it visible, student participants? Is it visible?
No, madam. Only slide is visible. Video content is not visible, ma'am.
Not visible. Okay. Okay. 1 minute. Is it visible now?
Yes, ma'am.
Okay.
In this video, we'll discuss why humans use comma filters. If you're not familiar with the topic, you may be asking yourself, what is a comma filter? Is it a new brand of coffee filter that removes the tasting coffee? No, it's not. A comma filter is an optimal estimation algorithm. Today we'll discuss two examples that demonstrate common uses of comma filters. In the first example, we'll see how a comma filter can be used to estimate a system state when it cannot be measured directly. To illustrate this, let's go to Mars before anyone else does. If your spacecraft's engine can burn fuel at a high enough temperature, it can create thrust that will let you fly to Mars. By the way, according to NASA, liquid hydrogen is a light and powerful rocket propellant that burns with extreme intensity at 5,500 degrees Fahrenheit. But be careful because at too high temperature can or anyone else does. If your spacecraft's engine can burn fuel at a high enough temperature, it can create thrust that will let you fly to Mars. By the way, according to NASA, liquid hydrogen is a light and powerful rocket propellant that burns with extreme intensity at 5,500 degrees Fahrenheit. But be careful because at too high temperature can put the mechanical components of the engine at risk. And this can lead to the failure of some of the mechanical parts. If that happens, you might be stuck in your small spacecraft where you got to eat from tubes. To prevent such a situation, you should closely monitor the internal temperature of the combustion chamber. This is not an easy task, since a sensor placed inside the chamber will melt. Instead, it needs to be placed on a cooler surface, close to the chamber. The problem you're facing here is that you want to measure internal temperature of the chamber, but you can't. Instead, you have to measure external temperature. In this situation, you can use a Kalman filter to find the best estimate of the internal temperature from an indirect measurement. This way, you're extracting information about what you can't measure from what you can. Now that you know the solution to your problem, you can continue your journey to Mars. But are you scared of traveling in space? Let me tell you this. On Mars, you're gonna weigh 62% less than what you weigh on Earth. Still not convinced? Okay, then let's go back and take a look at another scenario that takes place on Earth. In this example, we're going to see how a Kalman filter can be used to estimate the state of the system by combining measurements from different sources that may be subject to noise. You have guests visiting from overseas, and you need to pick them up from the airport. You're using your car's navigation system. Let's look at the sensors you have on board, which help you find your position and navigate you to the airport. The inertial measurement unit uses accelerometers and gyroscopes to measure the car's acceleration and angular velocity. The odometer measures the relative distance traveled by the car. The GPS receiver receives signals from satellites to locate the car on Earth's surface. If you live in Boston as I do, you've got to travel through the Big Big, a very, very long tunnel. And in the tunnel, it gets harder to estimate your position through GPS, since the receiver's line of sight to satellites is blocked and GPS signal is weak. In this case, you may want to trust the IMU readings, which give you the acceleration. However, acceleration itself doesn't tell you much about the car's position. For that, you need to take the double integral of the acceleration. Unfortunately, this operation is prone to drift due to small errors accumulating over time. To get better position estimates, you can use IMU measurements along with odometer readings. But note that odometer measurements may be affected by the tire pressure and road conditions. To summarize, your sensors measuring the relative position of your car give you fast updates, but they are prone to drift. The GPS receiver provides your absolute location, but it gets updated less frequently and it may be noisy. In this scenario, a Kalman filter can be used to fuse these three measurements to find the optimal estimate of the exact position of the car. Let's look at some facts about Kalman filters. The Kalman filter is named after Rudolf Kalman, who is the primary developer of this theory. It is an optimal estimation algorithm that predicts a parameter of interest, such as location, speed, and direction in the presence of noisy measurements. Common applications of Kalman filters include guidance, navigation, and control systems, computer vision systems, and signal processing. One of the first applications of Kalman filters was in the 1960s. Do you have any guesses as to what it helped with? Engineers used it in the Apollo project, where the Kalman filter was used to estimate trajectories of the manned spacecraft to the moon and back. Let's summarize what we've seen in this video. Kalman filters are used to optimally estimate the variables of interest when they can't be measured directly, but an indirect measurement is available. They are also used to find the best estimate of states by combining measurements from various sensors in the presence of noise. In the next videos, We'll cover what common filters are.
So, hope you understand this concept, participants. Is my screen visible?
Screen visible, ma'am, but the PPT is not visible.
PPT is not visible. Okay. Okay. Is it visible now?
Ma'am.
So, as mentioned, this Kalman filter is especially used for the um, linear applications, but most of the communication applications or biomedical applications, so they are the dynamics, the system dynamics are completely non-linear. So we will be using the different types of filters, Kalman-based filters, extended versions of the Kalman filters, and multiple Kalman filters, multi-modeling filters are also been used. So where the same principle is normally been used here also. So, participants, you can try this one, understand the aircraft dynamics. So you can try generating the state space modeling for this one. So here, if you observe for the aircraft dynamics, the states are used here U of t, W of t, like forward velocity perturbation and vertical velocity perturbation and pitch rate, pitch angle, altitude. So these are the input states, and so number of states even